Okay, welcome back. This is Mr. Hassan's Maths channel, and I'm now answering question number 6 from the June 2016 International, well, actually it's a GCE, the old syllabus, GCE, Edexcel Mechanics M1 exam, and this question is about moments. We've got a question about a non-uniform plank, AB, which has a length of 6 meters and a mass of 30 kilograms. The plank rests in equilibrium in a horizontal position on supports on the points S and T of the plank, where AS equals 0.5 meters and TB equals 2 meters. Now here they haven't drawn any diagram for us, which is kind of maybe on the rare side. So we have to draw the diagram ourselves. Anyway, so they're giving us some details. It says that when a block of mass m kilograms is placed on the plank at A, the plank remains horizontal and in equilibrium, and the plank is on the point of tilting about S. When the block is moved to B, the plank remains horizontal and in equilibrium, and the plank is on the point of tilting about T. The distance of the center of mass of the plank from A is d meters. The block is modeled as a particle, and the plank is modeled as a non-uniform rod. We've got to find the value of D and the value of M. So first thing we've got to do is to make a diagram. We've got to draw this diagram. So what I'm going to do is I'm going to just draw a diagram of a plank, just thin plank like this, and we're going to have supports. So it's 6 meters altogether. The width is 6 meters. So I will, yeah. So the total width from the start from the to the end is 6 meters. So that's 6 meters over there. So here we have 6 meters. Okay, that's the length of the plank. The plank is from A to B. AB, so the start of it is A and the end of it is B. Okay, and they're told it has some supports at S and T, where AS is 0.5 meters and TB is 2 meters. Okay, so you've got some supports. So I'll make this shape here. You got support at S and T. So let's say this is 0.5 meters. And I'll just copy and say this is 2 meters. So we've got here that's 0.5 meters and that's 2 meters. Okay, most of the questions that you find, they already draw them for you, but this is one where you have to draw them, so you should be ready for this in case it does come up. So that's 0.5 meters, that's S, and the other point is T. AS is 0.5 and TB is 2 meters. Okay, so that's S, that's a support at S, and that's a support at T. It's an S, not a 5. Let me make that a bit neater. That's a support at S, and that's a support at T. Okay, what else do we know? It says when a block of mass m kilograms is placed at A. So you got a block placed at A. So I'll just draw a block here, placed at A. Let's say that its weight acts at A itself. It's like treating it as a particle. Okay, so therefore its weight acts at one point, which is, we've been told to see that as A. So this is right over here, which take its mass acting right over there. Okay, and it's a mass m kilograms, so we don't know its mass, so its weight will be m times g. Okay. All right, when a block of mass m kilograms is placed on the plank at A, the plank remains horizontal and in equilibrium, and the plank is on the point of tilting about S when the block is moved to B. So let's consider this is the first case when it's at A, of course. That's the first case when the block is at A. All right. Now, what we don't know is it's a non-uniform plank. When it's a non-uniform plank, then the weight does not act through its geometric center. So I don't take the weight acting through 6 meters. They've told us about the weight, and they've told us that the distance of the center of mass of the plank from A is d meters. So we don't know where it is exactly. Somewhere over here, we don't know, we're just going to call it D. So I'll just take the distance, okay, as D meters. Let's say it's just somewhere over here. I don't know where it is. I'm just going to put it at a random place. So I'll say that this is where the weight is acting. Okay, just in some random place, the weight is acting over here, and it's D meters from A. So this is D meters, D meters. That's where the weight of the block, the plank. Now the weight of the plank is 30 G newtons. So this is 30 G newtons acting at this point here, which we don't know. We have to find this, but one of the things we have to find. Okay, so they gave us two situations. One situation they gave us is this situation where the block is at A, so mg is acting here, and in this case it says it's on the point of tilting about S, meaning it's about to tilt upwards like this. So if you put this weight here, okay, we have to find basically the value of m and d such that this thing will be about to tilt. So when it's about to tilt, it will basically, after it tilts, it will look something like this. This side will lift up. So when it tilts, okay, at the point where it's just about to tilt, it's on the point of tilting, meaning if you were to increase this mass anymore, or you were to increase this distance anymore, okay, then what would happen is it would start to tilt. Okay, it would start to tilt. In fact, this if it's going to tilt about here, then the distance is going to be somewhere over here, obviously. This is where D is going to be if it's about to tilt. So I didn't read the question first about the tilting. I know that the D must be somewhere over here, center of a mass. No, actually, it can be anywhere. We don't know. It can be anywhere. It can be anywhere. All right, it can be there. It just depends on how this is. So we don't know what D is. It could be anywhere, but we know that this will definitely be big enough for it to be about to tilt. So when it's on the point of tilting, then we can say that the reaction force at S is going to be equal to 0. You have a reaction force at S and a reaction force at T. When the support is in contact with the beam, there's a reaction between them. Now here we are considering only the forces that are acting on the beam, not the forces acting on anything else, just the beam. So I'm not considering the reaction force. Like, for example, some people say, why don't you put the reaction force on this block? Well, I'm not considering the forces acting on the block. I'm considering the forces acting on the beam. Okay, so that's where I'm not even considering the reaction force of the beam on the supports. I'm considering the reaction force of the beam of the supports on the block. So this is the reaction force at S, and this is the reaction force at T. Now, if it's about to tilt, then this is going to be 0, because this is about to tilt. Okay, no, if it's about to tilt about S, sorry, then the reaction force at T will be 0. So this is going to be equal to 0, because it's going to tilt about S. So the reaction force at T is definitely going to be equal to 0. So if that's the case, then we know the reaction force at S is going to be, well, we can't work out what it's going to be because we don't know the mass of the block. But what we can do is, this is 0, so that's eliminated. If we take moments about S, now taking moments about S will help us here. If we take moments about S, okay, if we take moments about S, we know it's in equilibrium and it's on the point of tilting, so this is 0. Taking moments about S will help us to eliminate this force at S, which we don't know what it is, okay, because it's the sum of these two, but we don't know what this is, so we don't know what that force is. So if we take moments about S, it will eliminate S from our equation, because the moments of the forces that are acting on S about S will be 0, because the distance of the force from S is 0. The moment is the distance times the force, the perpendicular distance of a point of the force from the point. So here what we're going to do is we have basically just the 30 kilograms which is acting in the clockwise direction. So the distance of S from this point, in terms of that, if we just sort that out here, okay, this force, this distance, sorry, here, which I'm going to have to use, is going to be d minus 0.5. This is d, which is the distance from A of this weight, of this of the weight, d minus 0.5. That is the distance from S. So that's a clockwise moments will be 30g times d minus 0.5 equals the anti-clockwise moments will be given by this. This is the clockwise and this is anti-clockwise. Here there will be no force, so therefore there's no turning effect from this because there's no force. Force is equal to 0, so it's about to tilt on there. So it's about to lift off from there, sorry. And you got this distance from S, which is 0.5, so this is equal to 0.5 times mg. So that's one equation we formed from about being about to tilt at A. Now the second situation is when it's about to tilt, when you move, it says when you move the force mg, okay, when the block is moved to B, then it's about to tilt, okay, on T. So in that second situation, everything else is the same. So what I'll do is I'll copy this situation and bring it down there. Okay, so this situation now, this block has moved to B. And this weight is now acting down at B. And in this case now, what's going to happen is it's about to tilt on T. Okay, it's about to tilt on T. Therefore, it's going to lift up from here. So RT will no longer be equal to 0. Okay, RS will be 0. So now in this case, what we're going to do is we're going to take moments about the point T. So if we take moments about T, all right, then we have the clockwise moments, which are going to be mg times 2, equal the anti-clockwise moments. If I'm taking about T, I need to find this distance, okay, which is going to be basically, that's going to be from there to there is D. So let's just have a look at this, try and figure this one out. I know from here to here is D. And I know that the distance from T here is, this is 2 meters. This is 2 meters. We need to know what this distance is. This distance is in terms of D. So let's work out what that is. All right, so here we got, that's what we're trying to work out now, this distance here in terms of D. So we can say that the distance that we need, this is 2 meters less than, so you have, this is 6 minus 2, 6 minus 2, so from here to here is going to be 4 meters. Okay, all the way across from here to here, it's going to be 4 meters. Okay, so let me just move these things out of the way a bit. Okay, so I know that from there to there is 4 meters. Okay, and from there to there is d meters. So this is going to be 4 minus d. This is 4 minus d will be the distance here. Okay, because that's 2 meters, that's 6 meters, so that's 4 meters. And from there to there is d, so this distance is 4 minus d. So it's going to be equal to 30 times g multiplied by 4 minus d. All right, so now I have 2 equations. I have 2 equations which I can now solve, and solving those 2 equations, therefore I'll be able to find the unknowns, which are d and m. Those are the 2 things that we don't know. Okay, so the point here is when you move the mass on this side, then this object is about to tilt on T, meaning this side will lift up from A. So the reaction force at S is going to be 0 at the point where it's just about to lift up. So it hasn't lifted up, but it's on the point of lifting up. So the reaction here has become 0. So you're finding the value of m, which will cause this reaction to become 0, but it's still in equilibrium. So it's in the point of losing its equilibrium. So we're saying that the total moments about any point is equal to 0. The sum of the clockwise and anti-clockwise moments will be 0 because it's in equilibrium. Okay, but the reaction force here is 0 at the same time, meaning it's at the limit of its equilibrium. Okay, it's at the limit of its equilibrium because that's when this is just about to lift up. Okay, so that's how we deal with this situation. So in the first situation, the weight here is such that it's going to cause it to lift up on, off this support and tilt, but it hasn't quite done so yet. It's on the point of doing so. So therefore, the reaction force here is going to be 0. And here, when you move it to this point here, then the opposite thing will happen. It will lift up off of S, but it hasn't quite done so. It's on the point, on the verge of doing so. So it's still in equilibrium, but the reaction force here is 0. That will give us the value of the largest possible value of M for it to happen. So what we're going to do now is we're going to take these two equations and we're going to solve them simultaneously. Okay, so we have one of them is 30g, so I'll write them on the next page actually, and then we'll continue there. Okay, so these two equations, when we solve these simultaneously, we should be able to find the values that we're looking for of S and, of M and D. Okay, so now let's just simplify this a little bit. So I'll write the first one as 0.5 mg equals 30 times G times D minus 15G. Okay, and the second one I'll write it as 2 mg equals, that's 120, 4 times 30 G. Okay, and that's minus 30 G times D. So I can see if I add these two equations together, if I add them together, what's going to happen is this is going to cancel out. So the D will be eliminated. Okay, so if I add them together, I'll have 2.5 mg is equal to, these two will add together, that's 120 minus 15, which is 105 G. These have cancelled out, so I can say M is equal to 105 G divided by 2.5 G. They cancel out, so I'm left with 105 divided by 2.5, which gives me 42. So M is equal to 42 kilograms. That's the mass. Okay, so that's M. And if you want to find what D is, we can use either of these two equations. So for example, I could use this equation here. I can say, is it easy to use in this form? No. Okay, I'll use this equation here. So I know that M is equal to 42 kilograms now. So therefore I can say 0.5 times 42 times G equals 30 times G times D minus 15G. So that's going to give me a half of 42, which is 21. So I've got 21G plus 15G equals 30GD. So 21 plus 15 is going to be 36. That's 36G equals 30 times GD. So I can say that the distance D, which is the distance of the center of mass from end of the plank, is going to be 36G over 30G. G's cancel out. We're left with 36 over 30. 36 divided by 30, which gives us 6 over 5, which is 1.2 meters. So we have M equals 42 kilograms and D equals 1.2 meters. That's the answer to part 1 and 2 of this question number 6. Okay, so this is all about moments and understanding this very important concept about tilting. So we have two situations. Okay, so I'll reiterate again because some student has been asking me this question. The first situation is that the mass is at A. When the mass is at A, it's on the point of tilting on S, which means it's going to lift off from T. It's just about to lift off from T, but it hasn't done so far. That's why it's still, the clockwise moments and the anti-clockwise moments are equal to each other, because it's still in equilibrium. Okay, anything that's in equilibrium, the sum of the moments about any point about that is always going to be the same, equal. All right, so they cancel each other out. So the clockwise and anti-clockwise moments, they will equal each other because it's in equilibrium. But it's just about an equilibrium. It's just about to tilt. That's why the reaction here, we take it as 0. Okay, and the second situation is where the mass has been moved to B, and now it's the reverse. It's about to tilt upwards like this. This is about to lift off from S, but it hasn't done so. It's still in equilibrium. The moments, that's why we can say the clockwise moments and the anti-clockwise moments are equal, because it's still in equilibrium, but it's just about to tilt. So therefore, the reaction force here is going to be 0. Okay, and we can make an equation using the clockwise and anti-clockwise moments being the same. And Taking moments about the support S in the first case is sensible because we don't know what the reaction force here is. Why? Because we don't know what this mass is. If we knew what this mass is, then we could take what's the word? We could take the moments about A, because we know what this force is, we know what this force is, we know that's 0, but we don't know what this mass is, therefore we don't know what the reaction force is. Why? Because this reaction force is equal to the sum of these two forces as once this has become 0. So taking moments about S is what we have to do. Why? Because it eliminates this force from our equation. Because if I take moments about S, any force going through S is going to have a 0 moment effect on that point. And similarly, in this case, we don't know what the reaction force at T is. Okay, so therefore taking moments about T will eliminate that from our moment equation, and we'll have, less unknowns, and we'll be able to sort out the question. So we got these two equations formed from those two situations, and then we solve those equations simultaneously, and we got our answers. Okay, so I hope that was clear. Other questions from this particular paper, June 2016. This is the GCE paper, not the IAL paper, the GCE paper 6677. Can be found in the playlist that will appear somewhere up here at the end of the video. Other questions which are about this topic of moments can be found in this playlist over here, and you can subscribe to my channel by clicking on this link. Thank you for watching. I hope you understood, and see you soon.